What's the limitation of the Fourier series? Only for periodic signals. So we're not always working with periodic signals, so it might not be absolutely useful for us every time. Although in practice, we use the FFT a lot in our daily lives, and the FFT is for periodic signals only. We just pretend we don't know. There's a generalization of the Fourier series for aperiodic signals. We just consider that an aperiodic signal is a periodic signal with an infinite period. So we have this rectangle here, and we're saying the period is increasing to a point where you just have one rectangle, and we will take advantage of the math of the periodic case. You can wait for the next rectangle, but you would have to wait forever. So you will not wait forever, but you know that if you did, you would find the next copy, so you can use the math. What happens when the period increases? I'm representing here n, not frequency. Notice that, for instance, the n equal to 20 is coming closer and closer in my representation. Because here the frequency, the range of frequencies that I am representing is constant. Okay, so regardless of the size of the period, the frequency here is the same for all instances that are being plotted. So when the period increases, the fundamental frequency decreases. So the spacing between you have this, here you have omega 0, 2 omega 0, 3 omega 0. Then if you increase the period, omega 0 decreases. And this comes to here, this comes to here, this to here. But the frequencies themselves are the same, right? Something else will come to here, but the frequency of this something else will be the same. So each n, when I increase the period, the frequency corresponding to a given n is smaller, but the frequency at that point is the same. Yes, I should have put frequency here, not n. So what happens with the spectrum when I increase the period? The spectrum becomes more dense, right? It becomes denser. What happens if I have a period of infinite size? The spectrum will be continuous. It will be so dense that this interval between the harmonics will be 0. Because this omega 0 equals 2 pi over T0, which is the period. So if the period is infinite, this is 0. This step is 0. So we will measure in the spectrum, we will have exponentials with for any real value of omega, right? Not only multiples of omega 0. Then we can achieve a formulation like this. The x of t will be an integral, not a sum. An integral of exponentials where I had e to the j n omega 0, it will be just j omega t, because now I have a continuous spectrum. E to the j omega 0 t. The coefficients were a function of n, right? Now they will be a function of omega. For each omega, in my continuous spectrum, I will have a coefficient, which is a complex number with a phase and a magnitude. And then I integrate across the spectrum. Here appears this guy, which is related to this. All the explanations that I know for the derivation of this from the Fourier series are oversimplified, and they take a lot of time nevertheless. So you can choose some explanation in the internet or in chapter 7 of Lathy's book, and you can follow it. But this is how we represent an aperiodic signal as a Fourier series. In this case, we call it the Fourier transform, not Fourier series. So this is the inverse Fourier transform. How do we find the values for x of omega? What do you think? This is this is an orthogonal basis. This is an orthogonal basis for signals, for aperiodic signals. Now we're doing inner products, not just inside one period, but from minus infinity to infinity. So we just did the same inner product from minus infinity to infinity. We would have to divide this by the infinite period, but actually, that is to multiply by 0, right? To multiply by some infinitesimal constant, which is actually here, dt. So calculus has these marvels. This guy is ensuring that these values tend to 0. They're actually becoming smaller and smaller here as I increase the period. So we do the inner product of x of t and the exponential, e to the minus j omega t. Minus j because in the inner product of complex vectors, we do the complex conjugate. And that's it. This is the Fourier transform. The Fourier transform. Let's go to the table. To the summary. So the Fourier transform ft, and also continuous time Fourier transform, CTFT. Synthesis, let's go. X of t is not a sum, but an integral. Equation. X of t is not a sum, but an integral, ranging from minus infinity to plus infinity of x of t, inner product with the exponential e to the minus j omega t dt. What did I miss? There's something wrong here. This is over omega. I'm integrating over the spectrum, not in time. Here is in time. Then the analysis, instead of coefficients dn, I'm getting continuous coefficients, if you like. Insert equation, continuous coefficients x of omega. There's no minus here. There's no. There's no minus. Let's do it all again. Synthesis. I'm looking for x of t, right? To synthesize x of t. Equation. X of t is 1 over 2 pi, 1 over 2 pi, integral coefficients x of omega. Each of them is multiplying an exponential with frequency omega. And I am integrating on omega.
The analysis too, the Fourier series analysis is also missing the t.
Yes. Is it? Yes. Here is dt. Integrating on t. Here, the analysis is the inner product. So, integral minus infinity to infinity x of t e to the, here goes the minus j omega t dt. So they're basically the same. The difference being that here I have a discrete spectrum. Here I have a continuous spectrum. So time domain, continuous. We're still working with continuous signals. Periodic, aperiodic. They can be periodic too. Frequency domain, continuous, aperiodic. Okay, Fourier transform. let's just do the Fourier transform of some signals. To keep it simple, let's do the Fourier transform of a rectangle. We're very familiar with the rectangle. So this is our signal, t, x of t, the very same rectangle that was inside a period of our periodic signal. It was ranging from minus 0.5 to 0.5. Amplitude 1. We can find a closed form solution for x of omega, which might be similar to what we found for dn, right? Let's go. X of omega equals we just have to integrate this from this to this, right? So five e to the minus j omega t dt. This comes dividing minus j omega e to the minus j omega t from minus 0.025 to 0.025. Same story. This e to the plus j omega 0.025. We swap the signs because of this minus. This is 1 over 40, right? Omega over 40. Yes, omega over 40. Minus e to the minus j omega over 40. So what I need we're going to use this. I need 2 here. I need 2 here, so I put 2 here. To j omega over 40. I need to divide this by 40. J2 oh It's just that. This omega comes here. So it's 2 divided by omega sine of omega over 40, which is 0.0 25 omega. Any mistake, or is it all right? So at this point, we usually define the sinc function, and we represent this as sinc. So we define sinc of x as the sine of x over x, which always appears when we're transforming rectangles. So let's represent this in terms of a sinc. So we need this argument to be here in the denominator. So this is omega over 40. We can do 1 over. We can do this. Omega divided by 2, sine of omega divided by 40, right? We're almost there. We just need to multiply by 20 here and here. So it's the sine of omega divided by 40 divided by omega divided by 40 multiplied by 20. So here's our sinc of omega divided by 40. So this is 1 over 20 sinc of 0.025 omega. I hope I did not commit any mistake. We can check in the table. We have table 6.1, which is Fourier series representation. Table 6.2, then we have table 7.1, Fourier Transform pairs. The Fourier Transform of the rectangle of T over tau. This is tau. Here tau equals 0.5. So this is the rectangle of T divided by 0.5. The Fourier transform, we represent Fourier transform with these arrows, should be tau sync, tau is 0.5. So 0.5 sync of omega tau, omega times 0.5 divided by 2.
It's actually 0.05.
0.5. 0.5. 0.5. 0.05, which happens to be 1 over 20. So everything turned out right. 1 over 20 sync of omega times 0.05. This is a function in the frequency domain. It's a function of omega. We can plot it to see what it looks like. Let's create a new Google Colab here. New notebook. New notebook. As always, we import NumPy and matplotlib. Then let's choose some range of frequencies. Okay, let's go at first from our signal. Let's go from -2 until 2 radians per second. A range -2 to 2 with this step. So our x of omega will be the sine 1 over 20 times, there's a sync function from NumPy, but it's too dangerous for us, NumPy sync, because it does not use the same definition of sync that we use. It uses the normalized sync, sine of x, pi x divided by x. It's too dangerous. Let's avoid it. Let's create our own sync function, sync of x. Return np dot sine of x over x. Sync of point 0.5 times omega. Let's plot it. Omega, x of omega. No, this shouldn't exist. Let's go from -20 to 20 radians per second. $200. better. 2000, even better. This is what the sinc function looks like. Let's go from minus 1000 to 1000. The sinc function is a sine modulated by 1 over x. We can actually plot the 1 over x here. Modulator will be this, we just divide by this. We take off the sine part. And then we plot it has to be I will get an error for omega equal NP. For 0, division by 0. Yes, how to avoid this? Yes. Things are right. I just have to adjust the axis. This goes here. If I do not plot the modulator, everything is all right. So we save the axis before plotting it. And after we plot it, axis. We recover the axis. Here. Then we don't see what's happening up there. This is the modulator, which is modulating the sine function. So this is the spectrum of that signal. We can also plot it as magnitude and phase, which is the most usual representation. So it has the same shape as this one. This was also a sinc. So it has the same shape. This is where this spectrum is tending to when I increase the interval. Also important is the Fourier transform of a Dirac delta. Let's do the Fourier transform of a Dirac delta. So x of t is this guy. Zero, zero, infinity. And here I represent 1 because it's the unit impulse. If I had 5 multiplying here, then I would put it at amplitude 5, denoting that it has area of 5. Fourier transform of this guy, I just plug it here. So for each omega, I'm taking the exponential, multiplying by this, and integrating. So I am basically multiplying the value of this impulse, the area of this impulse, by the value of the exponential at time 0. Right? So what I get as a result, this is actually one property of the Dirac delta. When I multiply it by another function, this is the property. Delta of t, I multiply by some function and integrate. What I get is this guy times f of 0, because it's where the function matters, because it's multiplying the arrow at 0. And I don't care about the values of the function for other values because they're being zeroed. So it's just the f of 0, which is a constant, modulating the Dirac delta, and this integral will give me f of 0. What if I have a shifted, I want to, if I do this t minus t0, f of t, then I'm just interested in the value of this function at t0, because this will be shifted. I just want to know what's the value of the function at t0. So essentially, this will give me f of t0. It's called the sampling property of delta of t. I get a sample of the function if I multiply by the Dirac delta and integrate. So from this property, this will give me e to the minus j omega 0, which is 1. So this is the Fourier transform of a Dirac delta. If you look at table 7.1, this is the pair number 6. It's there. If you have this in time domain, you have the constant 1 in the frequency domain, meaning that the spectrum is just constant. Every frequency matters equally when I want to synthesize a Dirac delta. If I integrate all possible exponentials, I get a Dirac delta. We're going to use this same property to derive the we're going to use it inside the inverse Fourier transform. So we did for the Dirac delta. Now let's check what's the signal that has this Fourier transform, a Dirac delta, shifted. So it's this spectrum here. X of delta is a Dirac delta here. It can be a unit impulse. It's at frequency omega 0, some arbitrary frequency omega 0. What's the signal that has this Fourier transform? Can we locate it in the table 7.1? Let's try to find it. It might be the pair number 8, right? The exponential. We can put this in the formulation of the inverse Fourier transform. X of t is 1 over 2 pi integral of the spectrum, which is this, e to the j omega t, from the sampling property of the Dirac delta, which works for any independent variable, not just time. This gets a sample of this function at this point, right? So I have e to the j omega 0 t. So it's the complex exponential with frequency omega 0 that has this Fourier transform. So this is the spectrum of this. It makes sense. This has just one frequency. So if I can break sines and cosines into exponentials, I will have some Dirac deltas. What did I miss here? Over 2 pi. So this is all linear, so I can multiply both sides by 2 pi, and I get this pair, as written in item number 8 of the table. Two pi delta of omega minus omega 0. Notice that now we are in the whiteboard because we don't want to do integrals in NumPy. We prefer to do summations. So here, functions are continuous in both domains, so we better work in the paper. Next one, what's the Fourier transform of cosine of omega 0 t? It's easy if we remember that the cosine can be recast like this. And we know what is the transform of this function. And one property of the Fourier transform, which is in table 7.3, the table of properties, is the addition. There's the scalar multiplication and then the addition. And both of them imply that the Fourier transform is linear. So I can do the Fourier transform of this, and then sum, and then multiply by half. And I get the transform of the cosine. So the Fourier transform of this, what's this?
Zero delta.
This delta of omega minus omega 0. It's a shifted delta. This plus omega 0, shifted to the left. There's 2 pi here, right? 2 pi. We can put it outside. 2 pi. Then half. So the spectrum of a cosine is pi times this. One impulse shifted to the right, one impulse shifted to the left. We can draw it like this. Magnitude pi, omega 0 minus omega 0. This one is here, this one is here. We can also find the Fourier transform of sine. There's just a j here and a minus here. So pi over j. There's a minus here. Minus here's over j. We can put this j in the numerator, right? In the numerator, and swap the signs. J pi. So we write this first. No, this first, plus omega 0 minus delta of omega minus omega 0. Is it right? Let's check in the table. Number 10. Yes, it's right. Sine of omega 0 t. Then what does the spectrum look like? The absolute value, the spectrum of magnitude is this. The spectrum of magnitude. But the spectrum of phase will differ. The spectrum of phase for the cosine is all 0. Because x of omega for the cosine had no imaginary part. Here I have plus j for this one, minus j for this one. Plus j means 90 degrees, right? Pi over 2. So the spectrum of phase is, I can put like a continuous function here. It will count only here, but I don't need to draw an impulse. I cannot draw an impulse because it's not infinite. It's pi over 2, and here minus pi over 2. So here is whatever, and here it's pi over 2. Here's minus omega 0. Here's omega 0. So this is the spectrum of magnitude, the spectrum of phase of the sign. What else? There's also the continuous, the aperiodic version of the Parseval's relation. In this case, it's for signals with limited energy. So we're computing energy, not power. It goes like this. To measure the energy of a signal, for instance, of our rectangle, we can measure its energy. We integrate the signal, its squared absolute value, dt. This is the measure of energy. It can also be integrated in the frequency domain. Squared. So these two integrals give the same result. One interesting thing is that the two integrals are very, very similar, right? There's just a complex conjugate here which is not there, and this scalar multiplication here. So there's one property, it might be listed here in table 7.2. It might be listed here. Duality. I will not write it because it's too misleading. You can compute a direct Fourier transform using the inverse Fourier transform formula and vice versa. Don't do it. But that explains things like we saw that the duality is the third one. We saw that the Fourier transform of a rectangle is a sink. What do you think is the Fourier transform of a sink, if we have a sink in time domain? If we have a sink of t, what do you think the Fourier transform will be? A rectangle. for sure. We have a Dirac delta in the frequency domain. We have an exponential in time. If we have a Dirac delta in the time domain, we got 0, right? We got 1. We did this pair. Right? So shouldn't we get an exponential here?
Times equals 0.
It is an exponential. This is, sorry, not equal. This is e to the j0 omega.
So for the zeros shift,
Yes, if we shift this guy, then we will find our exponential. I don't want to commit any mistake. Then we will get e to the minus j omega. Now it's omega, because here this is the independent variable, t0. So a Dirac delta in time domain. Actually, there's that property that we saw for Fourier series, that if we multiply the spectrum by this, we shift the signal in time. That's what we're doing. We're multiplying 1 by this. We're shifting the signal in time. So the duality property is real. You get one thing in time, another thing in frequency. Then when you get one thing in frequency, you get another thing in time. This will explain some other properties soon.